Hello and welcome to m200 Online Statistics at Cañada College. My name is Lapuz. In this video, we will do a homework from section 11.2. It says to conduct a hypothesis test and provide the test statistic, critical value, and p-value, and then state the conclusion. It says here that a person drilled a hole in a die and filled it with lead weight, then proceeded to roll it 200 times. Here are the observed frequencies for the outcomes 1, 2, 3, 4, 5, and 6 respectively. And then they have numbers here, 30, 28, 50, 42, 29, 21. They want us to use a 0.025 significance level to test the claim that the outcomes are not equally likely. Does it appear that the loaded die behaves differently than a fair die? So just by looking at this, I can see that there's a 50, there's a jump of a 50, 42 for the numbers 3 and 4, and then back to a 29, 21. So it looks like it goes up and spikes a little bit here for 3 and 4. And just by looking at it, I would guess that they might not be equally likely, but we should do a hypothesis test. We have the chi-square distribution table to help us find the critical value, but we'll take a look at that a little bit later. For right now, they want us to find the test statistic. So for this, we will take a look at StCr. Here's our StCr page open, and we don't have the original data, so let's go ahead and put that in. So the die value is 1, 2, 3, 4, 5, and 6. And unfortunately, we're not able to just copy and paste this, so we just have to type it in. So 30, 28, 50. Let's start off with 30. 28, and then 50, and then 42, 29, and 21. 42, 29, and 21. So those are our values. Now the die value is not really that important, but these are going to be the observed values that we have. Now we know that this thing was rolled 200 times, and so to find the expected values, we would divide each one by 200, or we would take 200 and divide it by 6 because that's the number of categories, and then we would normally fill up this var3 column, but instead we're going to have StCr do that for us. So here is the way to do a goodness of fit test using StCr. We'll go to Stat, goodness of fit. This is a chi-square test. Let's select that. Here we have the observed column. The observed column is going to be the observed value. The die value is just the categories. Now, if these things have a specific set of values, we would select the column that would represent the expected values. But since the expected values are all going to be the same, we're going to click on all cells in equal proportion. And we'll just build it here. Group. We don't need to do the group stuff, but we do want to highlight the expected value so that we can see the expected value in the next column. Okay, I think that's all we need. We'll compute. And here are the expected values. So I thought they were going to put it in the column, but they didn't. But it's essentially 33.33, and that's 200 divided by 3, or 200 divided by 6. Okay, what is important for us is the chi-square value. This is going to be your test statistic, and your p-value is 0.0047. Okay, so let's type in the test statistic, 16.9. We don't have to round off anymore because it only goes that far. Now the critical value, since we have StCr open, let's take a look at this critical value here. So the degrees of freedom is going to be the number of categories minus 1. So that's 6 minus 1, that's going to be 5. And we want a 0.025 significance level. So using the chi-square table, we can look at the value. This is going to be a right tail test. And we want the area to the right tail to be 0.025. And our degrees of freedom, remember, was 6 minus 1, which is 5. So if we take this number 5 and we go across until we get to the column, we're going to get 12.833. So I want to stay here for a minute, switch over to StCr, and show you how to find this using StCr. So using StCr, we're looking for a critical value in a chi-square distribution. So let's go to calculators, and choose the chi-square value. And we want the chi-square value, a standard chi-square value, and we want the degrees of freedom to be 5. And we want this to be greater than, and this is an unknown quantity for us. This is the number that we have to look for. And we want this number, the area, to be 0.025. So if we take this value, 0.025, that's the probability that we want. And we want to know what the marker is for this to give us a 0.025 area. So let's compute it. And we see that it's 12.8325. Okay, so that's the other way to find your critical value. So let's go back here. 12.833 is what they have. That's the same thing that we got. So I gave you two possible ways to do this. Oops, this is 12.833. One is to use a table, and then the other is to use the StCr calculator for chi-square. Now if we look at the test statistic, oh, by the way, the p-value, let's put the p-value in here. But before we go on, the whole role that the critical value plays is as a test statistic. So the test statistic is 16.9. If we go back to our picture here, and it's nice that StCr provides a picture, 16.9 is going to be somewhere in the red region, which is what we call the critical region. So if your test statistic falls in the critical region, then you're going to reject the null hypothesis. Okay? So that is equivalent to comparing your p-value with the significance level. So the p-value was 0.0047, but let me show you another way to find the p-value. Since we have the test statistic and since we have our chi-square calculator open, if we put in our test statistic in here, which is 16.9, and then we ask it to compute, we get 0.00469 or 0.0047. So they're all related. The p-value and the test statistic is related to the critical value and the critical region. Alright, so based on this, we saw that the test statistic was in the critical region. We also note that the p-value is less than significance level, and so in either case we will reject the null hypothesis. And when we reject the null hypothesis, we're going to be able to support the claim. So there is sufficient evidence to support the claim that the outcomes are not equally likely, and we kind of saw that the 50 and the 42 for rolling a 3 and a 4 looks like it was higher than the other values. So I think we can support the claim that the outcomes are not equally likely. The outcomes appear to be do not appear to be equally likely, so the loaded die appears to behave differently from a fair die. Okay, so it's a lot of logic involved in trying to read and parse through this these options to complete your sentence, but I think this is going to be correct. Let's check our answer. Okay, I hope that helps.